How are all of you? I hope you are fine. Have you seen the previous videos what I have uploaded in my YouTube channel? In today's class, we will see about magnets and related topics that is about production of a magnetic field. How magnetic field is produced from different materials and their characteristics and how a current carrying conductor of magnetic field seems like. Let's start from the first topic that is about magnet. What's a magnet? What do you think about magnets? A magnet, an object which is capable of producing magnetic field and attracting unlike poles and repelling like poles. This is the characteristics of a magnet. A magnet. Related to magnet, another very important concept is magnetism. What's magnetism? Magnetism is a concept introduced in physics to understand interaction between moving charges. The interaction between moving charges. To understand the interaction between moving charges, it is an attractive and repulsive phenomena produced by moving electric charge. Moving electric charge. This is a phenomena. It is either attractive or repulsive phenomena produced by a moving electric charge. Like the gravitational force, the electrostatic force, magnetic force is an interaction at a distance. As you remember, gravitational force is an interaction at a distance. Electrostatic force also an interaction at a distance like that. Magnetic force is an interaction at a distance. Magnetic field or a magnetic force is an interaction at a distance. What type of magnet do you know? What type of magnet do you know? We may divide types of magnets into three. That's the first one is permanent magnet, the second one is temporary magnet, and the last one is electromagnet. Let's see the first one. That is about permanent magnet. What is permanent magnet? Permanent magnets have their own magnetism and they are made up of ferromagnetic materials like iron or nickel. This is a permanent magnet that is commonly used magnet because they do not lose their magnetic property once they are magnetized. Once they are magnetized, they will not lose their magnetic property. So they are called permanent magnet. Permanent magnet. What about temporary magnet? What is temporary magnet? Temporary magnet can be magnetized in the presence of a magnetic field. When the magnetic field is removed, the materials lose their magnetic property. They will lose their magnetic property if we remove the source of their magnetic nature, that is the magnetic field. The best example is iron nails and paper clips are examples of this temporary magnet. Temporary magnet. The other types of magnet is electromagnet. What is electromagnet? Electromagnets are coils which produce the magnetic field when an electric current passes through the coil. Such types of magnets, what we call electromagnets. Electromagnets. This consists of a coil of wire wrapped around the metal core made from iron. When this material is exposed to an electric current, a magnetic field is generated, making the material behave like a magnet. They will behave like a magnet. If the current is passing through that coil will act like a magnet. And the strength of the magnetic field can be controlled by controlling the electric current. Controlling the electric current passing through this coil, we can control the strength of the magnetic field. These electromagnets are utilized in various industries for various production and manufacturing process. Well, it is applicable at different industries for different production and manufacturing process, including in motors and generators. These electromagnets are applicable. How this production magnetic field is produced? How this magnetic field is produced? Magnetic fields are produced by permanent magnets or by electric current flows through the conductor. That is by electromagnet, either a permanent magnet or electromagnet. These magnetic fields may be produced. Like the electric field, a magnetic field may be considered as being a medium by which the forces are transmitted. The forces are transmitted. The force of magnet will be transmitted, that is either attraction or repulsion. It will be transmitted from this field. Have you imagined the magnetic field, what it seems like, especially in the permanent magnet or in the electromagnet? Have you seen? Have you wondered? Okay, let's show you some animations about the field. Have you seen here? This is a north and south nature, so it will interact. It will interact. It seems like this. The field seems like this one. The magnetic field seems like this one. As you can see here from this video, it is coming out of the north pole and enters to the south pole outside the magnet, and inside some magnet it is moving from south to north. So this is the field what it seems like, the magnetic field what it seems like. The other topic related to this is magnetic field characteristics. What is the characteristics of this magnetic field? We have seen what it seems like, including the animation, what a magnetic field seems like, but what characteristics have this magnetic field? As you have already seen in the animation, they always form a complete closed loop. They always form a complete closed loop. Unlike a line of electric flux, which radiate from and terminate at the charged surfaces, as you remember, electric flux is started from the positive charge and it will terminate from the negative charge. But when you come to here, in the magnetic flux, they always complete closed loop. They always complete closed loop. The other characteristics is in the space surrounding a magnet, the lines of the force radiate from the north, as you have already seen from the animation. It will radiate from the north and complete to the south. In the space surrounding a magnet, the lines of the force radiate from the north pole to the south pole. The other characteristics of this magnetic field is they behave as if they are elastic. That is, when they distorted, they try to return to their natural shape and spacing. They will never intersect each other. These fields lines, they will never intersect each other, and like poles repel and unlike poles attract each other. As you can see here, this is north and north pole, so they are repelled, and the field lines are out coming from the north and going to the south pole outside the magnet, so they are repelled. But when you come to here, the unlike poles, they are attracted to each other. It starts from the north and it ends at the south pole. This is some of the characteristics of this magnetic field lines. What is the magnetic field due to a current carrying conductor? In the current carrying conductor, which type of magnetic field is available? What is the characteristics? What is the characteristics of the magnetic field around a current carrying conductor is our topic right now. Generally, a magnetic field can be interpreted as a region where the force of magnetism acts. A region at which a force of magnetism acts may be called a magnetic field. A magnetic field. I recall that current is defined as the rate of flow of charge. Current is the rate of flow of charge. The stationary charges produce an electric field which is proportional to the magnitude of the charge. As you remember from Coulomb's law, the stationary charges, especially electrostatic charges, produce electric field which is proportional to the magnitude of the charge. That is the product of, as Coulomb's law states, the product of their magnitude directly proportional to the product of their magnitude and inversely proportional to the square of the separation distance. So stationary charges produce an electric field which is proportional to the magnitude of the charge. The same principle can be applied here in the current carrying conductor. Moving charges produce magnetic field which are proportional to the current. Therefore, a current carrying conductor produces magnetic field around it. It will produce a magnetic field. A magnetic field, as you remember, has both magnitude and direction. It is a vector quantity. And we can represent by B. This indicates the magnetic field. So how can you determine the magnitude and the direction of this magnetic field? If the magnetic field is a vector quantity, it will have both magnitude and direction. So how can we get the magnitude and how can we get the direction is the next issue. Magnetic field due to a current carrying conductor depends on the current in the conductor and the distance of the point from the conductor. That is the same to that of Coulomb's law. The direction of the magnetic field is always perpendicular to the current carrying conductor. It is always perpendicular to the current carrying conductor and it will be determined by the right hand rule. As you can see here in this image, by If you wrap your right hand's fingers around the current carrying wire and your thumb point in the indicate in the direction of the current. Your thumb here is your thumb indicates the direction of the current, then the direction in which these fingers, the direction in which the fingers will curl will give you the direction of the magnetic field. This is the direction of the magnetic. If the current is moving from this point to this point, the direction of the magnetic field is always perpendicular to the current carrying conductor, and its direction will be determined by the right hand rule. How can we determine the magnitude? The magnitude. The magnetic field strength is produced by a long straight current carrying wire is found by experimentally to be the electric field, which is equal to the permeability times current divided by 2 pi r, where I is the current through the wire, r is a shortest distance from the wire, and mu naught is the permeability of free space, and B is the magnetic field strength. So we can determine the magnitude according to their separation distance from this wire, and the direction can be determined by the right hand rule. What if the current carrying conductors are connected, in parallel, either it may be the current may be in the opposite direction or in the similar direction. How can we determine? Here we are determined only the magnetic field due to a single current carrying conductor. But how it will be if the current carrying conductors are in parallel? We can use this formula. Magnetic flux density due to the current carrying into long and parallel straight conductors where current flows in the same direction, like this one. In the same direction, the magnetic field will have the same direction, so it will be additive. So the total magnetic flux density will be mu naught I divided by 2 pi r plus mu naught I over 2 pi into x minus a. This is x minus a is in between the separation distance. So since we have already calculated it, it will be additive. But what if the current is flowing in opposite direction, like this one, in the opposite direction, the one conductor is a current flowing from this point to this point, and the other conductor, the current is flowing from this point to this point. If this is the case, we will use this formula. If it is the case, we will use this formula. What characteristics of magnetic field due to current carrying conductors? What are the characteristics of this magnetic field due to current carrying conductors? The first one is it encircles the conductor. As you can see here, it encircles the conductors. This is a current carrying conductor, so it will encircle the conductors itself. It lies in plane perpendicular to the conductor. A reversal in the direction of the current flow reverses the direction of the field. As you remember, the direction of the field is determined by the right hand rule. So the thumb will indicate the direction of the flow current. So if the direction of the flow current is changed, the magnetic field, the strength of the field, the magnetic field direction will be reversed. The other property is the strength of the field is directly proportional to the magnitude of the current. As you remember from the previous formula, it will be directly proportional to the magnitude of the current. The strength of the field at any point is inversely proportional to the distance of the point from the wire. This is the distance of the point from the wire. So from this equation, the distance of the point from the wire is inversely related within its field. Okay, up to now, we have seen that the straight wire current carrying conductor will have a magnetic field. But what if the current carrying conductor is a loop? If it is a circular, what will be the magnetic field? Magnetic field due to a current through a circular. Suppose the straight wire is bent in the form of a circular and a current is passed through it. How would the magnetic field look like? Have you imagined? We know that a magnetic field produced by a current carrying straight wire depends inversely on the distance from it. We have already seen the equations related to the distance. Similarly, at every point of the current carrying circular loop, the concentric circles representing the magnetic field around it would become larger and longer as we move away from the wire. Here it is a circular loop. So while we are moving away from a circular loop, this is becoming a straight line. A straight line. That means it is decreasing. And nearest to the conductor, it is a small and circular loop. Every point of a current carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. It's larger and larger, larger and larger. At the center of the circular loop, the arcs of this big circle would appear as a straight line. You see, this appear as a straight line. The circle, it will be appear as a straight line, Every point on the current carrying wire would give rise to the magnetic field appearing as a straight line at the center of the loop. By applying the right-hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction with the loop. As you remember from the previous topics, we will determine the direction of the magnetic field by a right-hand rule, that is by the thumb will indicate the direction of the flow of current and the fingers will curve in the direction of the magnetic field, So if you see here, each point will contribute to the central part. By applying the right-hand rule, it is easy to check every section of the wire, contribute to the magnetic field lines in the same. So it seems like this one. Every point will contribute to the magnetic field lines in the same direction. So it seems like this one. We know that the magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Directly on the current passing through it, if you remember from the formula. Therefore, if there is a circular coil having n number of turns, the field produced is n times as large as the produced by a single turn. If the number of turns is n, it will be n times larger. This is because the current in each circular turn has the same direction and the field due to each turn then just adds up. Just adds up. So if I have the number of turns, which have n number of turns, it will increase the field strength. Okay, this is all about today's class. If you have any question, you can put on the comment box. Thank you very much for your attention.